Good morning and welcome everyone to today's lecture. Today's lecture is lecture number 5. And if you remember, we were dealing with refraction at plane surfaces. In the previous class, we had seen what happens, what is refraction. We have seen the laws of refraction. We have seen that sin I by sin r is mu r by mu I, that is equal to vi by vr. I hope all of you remember this relation. Sine of angle of incidence divided by sine of angle of refraction is equal to refractive index of the second medium divided by refractive index of the incident medium, that is equal to the speed of light in the incident medium divided by the speed of light in the refracted medium. This is also known as Snell's law. We have also seen refraction at plane surfaces. When you have a slab and you have a ray incident on the slab, one ray is getting emergent, and we have seen that the incident and the emergent ray are parallel to each other. We have also seen the lateral shift, and the lateral shift is d upon cos r into sine of 1 minus r. Do we remember this?
Yes, sir.
And the last thing I think that we saw was the shift. When I say the shift, what do I mean? When you have an object on the other side of a slab and you are viewing from the second side, you will always see what? You will always see that the object is shifted. And remember, the object is always shifted towards the slab, and the shift in the slab, shift in the object, the shift of the object towards the slab is given by this formula. Do we remember this formula?
Yes,
Shift
sir.
when the object is seen from the other side. And if I can show you the diagram once again, I will show you the diagram once again so that you are reminded completely of what I am talking about. This is what I am talking about. The object is here, but when I watch it from the other side, this is the other side, I will see the object here. The object shifts by a distance x. This distance x is d into 1 minus 1 by mu, where d is the thickness of this slab. Do we all remember this?
Yes, sir.
Okay, so now let us start today's class, and we will start today's class by some important points. All these important points will be coming as question in your paper. We have seen real depth and apparent depth. Similarly, whenever you see an object inside any liquid, any other medium, it will appear to be bent. If I have this pen, and if I dip some part of this pen in water and I see it from outside, it will not appear straight. The part which is inside water will be appearing bent. Do we understand this?
Yes, sir.
So how much it will appear bent, or what will be the apparent depth? Remember, I have given you the formula. I have given you the formula. D apparent is equal to D real. Remember that formula? Into incident ray ka refractive index divided by refractive index of the refracted medium. You can also apply this formula here. I told you that this formula is applicable, the universal formula, whether ray of light is going from rarer medium to denser medium, or it is coming from denser medium to rarer medium. Do we remember this?
Yes, sir.
And again, I'm showing you the diagram from your sheet where you can see the object being bent. This is how the object is bent. As you can see, this depth, this depth, this depth is the real depth, and this depth with what you see is the apparent depth. Do we understand this?
Yes, sir.
And this apparent depth is real depth into refractive index of air, that's the incident medium, divided by refractive index of water, which is the refracted medium. Can I have some raised hand that we understand what I am talking about? The next illustration or the next use or where we see refraction coming into the picture, and you must just note it down in the sheet, is twinkling of stars due to fluctuation in the refractive index of atmosphere. The refractive index of atmosphere, as you go up or down, it keeps on changing. The fluctuations becomes irregular, and sometimes when the light that is supposed to come from the star will get refracted differently because the refractive index fluctuates. We will see sometimes light coming, we will see sometimes light not coming, and that is how, that is why, that is the reason that we see twinkling of stars. Do we understand this?
Yes, sir.
So these are the two phenomena. Remember, whenever you get a question, what is the reason for twinkling of stars? You will get 3 or 4 options. The correct option would definitely be refraction of light and difference in the refractive index or fluctuation in the refractive index. Shall I move ahead? Have you marked it down in your sheet? You can only mark it out in your sheet. There is no point of writing it because you can remember it by marking in the sheet. Can I move further ahead?
Yes, sir.
Well then, these are the points which you are supposed to note down in your notebooks. Number 1, mu, refractive index, is a scalar quantity. It has no units and dimension because it is the ratio of two speed. Wherever there is a ratio, whenever you call it ratio, ratio is a number, does not have any dimension, it does not have any unit. Do we understand this?
Yes, sir.
If mu naught and epsilon naught, mu naught is known as permeability of space or magnetic permeability, and epsilon naught, you must have heard in the chapter on electrostatics, is the absolute permittivity of vacuum. Then you can have this relation, the refractive index can be written in this form. Refractive index of that medium would be c divided c, which is the speed of light in vacuum, divided by v, which is the speed of light in the medium. This is the relation. This is how you can find the speed of light in vacuum. Remember, this is a relation. C is 1 by root over epsilon naught into mu naught. Similarly, v, the speed of light in that medium, will be 1 divided by root of epsilon into mu, where epsilon is the refractive, is the permittivity of that medium. Mu is the permeability of that medium. If you divide these two, this is the formula that you are getting. It's a very, very important formula. A question straight away from this formula would be asked in the examination hall. Remember all those variations. I'll give you a minute to note these things down. Well, then this is the next point which we already know. The refractive index of free space or vacuum is minimum and the value is 1. Refractive index of any other body will be more than 1. Please note it down. Here comes the first question, and let me have your answers, please. When a ray is refracted, what are the options that happen? 1, 2, 3, 4, A, B, C, D. And the correct option is, we don't have a correct option? No one knows the answer?
Option C, sir.
When a wave is refracted, its path must change, its amplitude must change, its velocity must change, its frequency must change. So what is the option? Its
Velocity.
velocity must change. Do we understand this? Yes or no? No or
Ye-
yes?
yes, sir.
When its velocity changes, it gets refracted, it bends towards the normal. Okay, well done. These are the type of questions we are supposed to encounter, and this is the next one. Let's see who gives me the answer for this one. Question number 2, and here it comes on your screen now. A ray of light passes through a pane glass slab of thickness T. Refractive index is mu, which is 1.5. The angle between the incident ray and the emergent ray is, and what is the answer? A, B, C, D. 1, 2, 3, 4. Anyone with an answer? No one knows the answer. A ray of light is passing through a glass slab. Plain glass slab. What is the angle between the incident ray and the emergent ray? Sad, no one knows this. It's sad that I have told you that 3 times at least. The angle would be 0 because the incident ray is parallel to the emergent ray. Do we remember this?
Yes, sir.
What is the use of remembering when you cannot tell me that you cannot tell me the answer? Please don't do this, beta. You are doing a lot of hard work, and most of the questions that are going to come, out of 50 questions that are going to come, around 30 to 35 questions are going to be of this nature, where they are going to test your remembrance, whether you remember things or not. And if you don't remember things and you become gajnis over there, well, I'm not going to come and get myself cured in whatever hospitals you are working in. Question number 3 comes. Let's see who has the answer for this. When a ray of light enters a medium of refractive index mu, it is observed that the angle of refraction is half of the angle of incidence. What is the angle of incidence? I'll give you 30 seconds. So, what is the option?
A, sir.
Option A. How did you get option A? How did you get cos? How did you get it? कौन बनेगा करोड़पति? Guessing?
Angle of reflection for full 2 cos theta
What,
inverse
beta?
u.
What? Tell me.
The angle of refraction for the full incident is 2 cos theta mu, sir. For the off, it is 2 cos theta mu by 2.
Angle of incidence for full is 2 cos mu. How did you get that? From where did you get that? From where did you get it? Is there any formula that tells you this? Well, Is there any formula that tells you this? Angle of refraction is half of the angle of incidence. How did you get this? The if you know the answer, it's very good. But how did you get to that answer? That is what my reason, that is what my question is. So what I'm going to do, observe that the angle of refraction. So I apply Snell's law. Snell's law is sine I by sine of R. Here R is I by 2. Do we understand this?
Sir.
Is equal to mu of R, the refracted medium, which is equal to mu divided by mu of air, which is the incident medium. Mu of air is 1. So sine I by sine R becomes mu. We understand this, everyone?
Yes, sir.
Now here it is sine of I by 2. Here it is sine of I. How do I solve this? I use the double angle formula. What is the double angle formula? Sine of 2 theta is 2 times sine theta cos theta. Do we understand this? That is maths. So I apply the double angle formula. I convert sine of I into sine of I by 2. How do I do it? I use the formula, and let me write the formula in the sheet because I don't have space here. So I'll just use my sheet, and here comes my sheet on your screens now. So what I'm gonna do is I'm going to write the formula of sine of 2 theta. Do you know the formula of sine of 2 theta? Theta is the angle. The formula is 2 times sine theta cos
Cos
theta.
theta 2.
Will you remember this?
Yes, sir.
Great. If you can remember this, then what I'm going to do, I'm going to write the formula again. Sine of I divided by sine of I by 2, because angle of refraction is I by 2, is equal to mu. This is where we were in the question. Now I just use the double angle formula in the numerator. So I'll write it like this: 2 times sine of I by 2 multiplied by cos of I by 2. Do we understand this? What I have done, everyone in the class? Can I have some raised hands from everyone who's sleeping in the class and everyone who's listening to me in the class? Who all sleeping? Please raise hands. No one is sleeping. Everyone was sleeping. Everyone raise hands. Divided by sine of I by 2, that is equal to mu. Now it is simple maths. This will get cancelled. This 2 will come in the denominator here. So what do I have in the next step? Cos of I by 2 is equal to mu by 2. Is everyone there with me up till here? Again, I will have to apply more maths. So I get to the next steps. I by 2 will be equal to cos inverse. I hope you know inverse function. Cos inverse mu by 2. And now I come to my last step. I is equal to 2 times cos inverse mu by 2. Remember, you might not get so much time to solve this question in the examination hall. Either you remember how to solve it, or as someone said, that you remember the answer of how it is solved and what is the answer. Do we understand this? Can I have raised hands?
Yes, sir.
I'll give you a minute to note this thing down before moving on to the next question. 30 seconds. Well, here comes the next question, and let us see who can give me the answer to this one. And the question is, mu r and epsilon r are the relative permeability and dielectric constant, relative dielectric constant, or dielectric constant of a medium. Its refractive index will be given by what? How do I get the refractive index from relative permeability and relative permittivity, or people also call it dielectric constant? Can I have the answer, please? A, B, C, D, 1, 2, 3, 4. And I had given you this question in the notes only. The answer is option
C, sir.
option C. Remember this formula, beta.
N is equal to C by V.
Yes, yes, yes. You can use this formula. And then this question, I have seen a lot of students getting confused in this one. Here comes the next one. Light travels through a glass of thickness T and refractive index mu. If C is the velocity of light in vacuum, what will be the time taken by light to travel through the plate? I've seen a lot of students getting confused in this question. That is why I'm asking you this. And same question might come in the examination hall. I'll give you a minute to think about it, not think it about. So my dear friends, do we have any answer for this one? No? Well, very sad. Time taken.
Option C, sir.
Option C is the correct answer. That is the correct answer. How do you get it? Light is going to travel with a constant speed. Distance is t. You have to distance is d. You have to find out the time traveled. Time travel will be distance divided by velocity. Yes or no?
Yes, sir.
Distance is given as t. Velocity of light in that medium will be c divided by mu. Yes or no?
Yes, sir.
This velocity will be c divided by mu. We have seen it many times. Just divided by c divided by mu. Mu comes in the numerator. Mu into d divided by c. D is given as t, thickness. So mu into t divided by c. That is the answer. Can I have raised hands from everyone that we have understood this?
Yes, sir.
Okay. Then we move on to the next question, and the next question pertains to what we did at the last part of this chapter, I mean of the last class, and I will be very happy if you can give me the answer to this one. The question comes on your screen right away. The bottom of a container is 4 centimeter thick glass slab. The container contains, so basically you have the bottom of a container is thick. It's made up of glass and it is thick. It is 4 centimeter thick. The container contains 2 liquids of depth 6 and 10 centimeters. What is the shift of the scratch on the outer surface of the bottom glass slab? Oh. When viewed through the container, it might look very difficult, but see, if this is the container, this is the bottom of the container, there is a scratch here, and this bottom of the container is basically thick. It is 4 centimeter thick. Then we have one liquid which is 6 centimeter thick or depth. Then we have other liquid which is 8 centimeter deep. You have to find, if I wash the scratch from the top, how much does the scratch shift? How much does the scratch shift? How much does the scratch shift? I'll give you a minute to note to solve this question. You can easily solve this question if you understand what the question is all about. So I will just draw the diagram. This is the container. This is the bottom of the container, blue. Bottom of the container, blue. It is of thickness 4 centimeter. So I write 4 here, and the refractive index is 1.5. Do we understand this? Can I have raised hand that we understand this?
Yes, sir.
Then I have the second layer, which is the layer of A. The red one is A. The thickness of A is 6 centimeter and the refractive index is 1.4. Do we understand this?
Yes, sir.
Then I have the third layer. The third layer is of the liquid B. The depth is 8 centimeter and refractive index is 1.3. Do we understand this?
Yes, sir.
Now I have a scratch mark here. This is the scratch mark. AB is the scratch mark and I am going to observe it from here. Do we understand this?
Yes, sir.
So how much does it shift? So basically this question now becomes, what is the shifting? Now how do I find the shifting? I know the formula of shifting by one slab. Yes or no? I
Yes,
know
sir.
the formula of shifting by one slab. And as you can see, this is the formula of shifting by the first slab. Yes or no?
Yes, sir.
This is the formula of shifting by the second slab. Yes or no?
Yes, sir.
This is the formula of shifting for the third slab. Yes or no?
Yes, sir.
I've added all these three because all these three shifts will be towards the slab. Yes or no?
Yes, sir.
I just put the values, I get the answers, and I stay happy. D1, this is D1, this is 4. Mu1 is 1.5. Do we understand this?
Yes, sir.
Then we have D2, which is 6, and mu2, which is 1.4. I put it there. Then I have D3, which is 6, and mu3, which is 1.3. I just put the formula, solve the equation, get the answer, and I stay happy ever after. I'll give you a minute to note this down. Then let's move on to the next topic. And the next topic is a very important one. Please mark it. It's a very important topic, which is known as total internal reflection. Now, what do I mean by total internal reflection? What do I mean by total internal reflection? Any idea? Reflection. I mean, we were on the topic of refraction. From refraction, we have jumped on to reflection. Why have we jumped on to reflection? Why have we jumped on to reflection? Now remember, what happens when when light travels from denser medium to rarer medium? What happens when light travels from denser medium to rarer medium? Denser medium speed is less, refractive index is more. Rarer medium speed is more, refractive index is less. The light will bend away from the normal. Yes or no?
Yes, sir.
Now, if you keep on increasing the angle of incidence, the angle of refraction will also be increased. Yes or no?
Yes, sir.
Because sine I by sine R is a constant. If you increase the angle of incidence, the angle of refraction also increases. Now, what can happen at a particular angle of incidence? The angle of refraction becomes 90 degrees. For one particular angle of incidence, the angle of refraction becomes 90 degrees. This angle is known as the critical angle, IC or theta C. C standing for critical. This angle is known as critical angle. Now, if I have the angle of incident light more than critical angle, what will happen? The rays will not be refracted, the rays would be reflected. If I have the angle of incidence more than the angle of critical angle, the rays will not be refracted, the rays would be reflected back in the same medium. This phenomena is known as total internal reflection. Do we understand this?
Yes, sir.
I will give you a minute to note it down, and after that I'll show you a diagram where it will be clear what is total internal reflection. Just again I repeat it. When the light goes from denser medium to rarer medium, it bends away from the normal. If I increase the angle of incidence, angle of refraction also increases. At one particular angle of incidence, angle of refraction becomes 90 degrees. This angle is known as critical angle. If your angle of incidence is more than the critical angle, light will not be refracted. Light would come back into the same medium. This is known as total internal reflection. 1 minute to note it down. And this is the diagram I was telling you about. What you have to understand in this diagram. I hope that you are drawing this diagram. As you can see, the object, oops, wrong color. The object, which is the light, is in denser medium. Do we understand this?
Yes, sir.
So light is traveling from denser medium and the second medium is rarer medium. Yes or no?
Yes, sir.
Now you can see it is bending away from the normal, the blue light, the blue ray, which is the refracted ray, and the red ray. The blue ray has refracted away from the normal. Yes or no?
Yes, sir.
Here, as you can see, the angle of incidence is less than the critical angle. This is the angle of incidence. Upar wala is the angle of refraction. Angle of incidence is less than the critical angle. So what is happening is that you are seeing light getting traveled or light traveling from one medium to the other medium. Light is getting refracted. Can I have raised hands from everyone that we understand this? Okay. Now what happens is that at one particular angle, where the angle of incidence is critical angle theta c or IC, the angle of refraction, the blue one, becomes 90 degrees. Do we see this? So the blue ray will just go like this. Do we understand this?
Yes, sir.
This angle where the angle of refraction becomes 90 degrees is known as critical angle. Will you remember this?
Yes, sir.
Then we go to the third case. In the third case, you can see the angle of incidence is more than the critical angle. So what do you see, my dear friends? This is the wrong diagram. The light will not go like this. The light will go like this in the blue direction. It will not pass into the second medium. It will come back into the first medium. This phenomena is known as TIR. TIR, total internal reflection. Do we understand this?
Yes, sir.
You will have 1 minute to note this down, draw this diagram, all the three cases. I'll be back in a minute. I hope you have noted it down. Then we shall move on to the conditions for total internal reflection. Remember, there are two conditions. Total internal reflection can only happen, condition number one, when light is traveling from denser to rarer medium. It cannot happen when it travels from rarer to denser medium. It can only happen when it travels from denser to rarer. Do we understand this?
Yes, sir.
Then the second case is angle of incidence I must be greater than the critical angle. Do we understand this as well? Two
Yes.
conditions, two conditions, two conditions, two conditions, two conditions.
Yes, sir.
Note it down. These two conditions, I'll give you a minute to show me your talents. Well, then comes the next heading, and the next heading is this. What is the relation between critical angle and refractive index? And what is the relation between critical angle and refractive index? Sine of critical angle is 1 by mu. Never forget this. Never forget this. Sine of critical angle is 1 by mu, and 1 by mu is inversely, or 1 by mu is proportional to lambda. So critical angle for red light, which has got more wavelength, is more, critical angle of violet light which has got less wavelength is less. Do we understand this?
Yes, sir.
Can I have some raised hands from everyone in the class that we understand it? I'll give you a minute to win it from here. Then this thing, sir, for total internal refraction, your angle of incidence should be greater than critical angle, yes or no?
Yes, sir.
That means sine of angle of incidence should be more than the critical angle. Now, sine of theta c is equal to mu, 1 by mu. So 1 by mu should be greater, 1 by mu should be less than sine of critical angle. So basically, this is what the relation comes for total internal reflection to happen, 1 by sine I. This is the first way of writing this, or sine of I should be greater than sine of critical, or 1 by sine I should be less than the value of mu. Then they have given us an example when light travels from grass to air. The critical angle is 1 divided, sine of critical angle is 1 divided by 3 by 2. It is 2 by 3, somewhere around 42. If angle of incidence is greater than 42 degrees, total internal reflection will happen. If it is less than 42 degrees, the rays will get traveled from glass to air by refraction. If it is exactly 42 degrees, the angle of refraction would be 90. Do we understand this?
Yes, sir.
I'll give you a minute to note it down.
Yes.
Well,
sir.
then we come to these illustrations of total internal reflection. Diamond, you must be knowing that diamond is not as costly as it is made to be. In fact, it is also not a rare commodity. Gold is valuable because it is rare. Diamond is available in abundance. Do we know this? Yes or no? Diamond
Yes,
is
sir.
not valuable because it is rare. I mean, it is available very easily. You can have this much big piece of diamond, but it may not be even 2 rupees. What makes it worthy is sparkling, the way it is polished and it is shine, and the diamond sparkles without because of total internal reflection. Do we understand this?
Yes, sir.
The point that makes it costly is not because it is rare, it's because the refractive index of diamond is 2.5, the angle is 24 degrees, so we can make a total internal reflection happening inside it. If you are cutting the diamond, and that's what makes it valuable, it's not the rarity, it is available in abundance in kilos. If the angle of incidence is more than the critical angle, total internal reflection happens again and again. The light which beams out from a few places where it comes out makes it sparkle, shining. Diamonds are the best friend of girls. That is what it said. Boys also wear diamonds these days. It sparkles, so it becomes costly. It becomes costly because of total internal reflection, because of the cutting. So diamond cutting is the main job. Diamond is very, very common. It's not rare at all. Do we understand this?
Yes, sir.
Optical fiber, and right now the Wi-Fi that I'm using is optical fiber. So they have laid optical wires up till my home, and from their box again an optical fiber is coming to my Wi-Fi thing here, Wi-Fi router, and then through the router I'm showing you this class. You will be also using this optical fiber when you want to see inside the stomach. You put a danda. It's not a danda, it's an optical fiber that goes inside, and you can see what is happening inside. This is because of optical fibers. And why they are not optical fibers? Because they use the phenomena of total internal reflection. As you can see, this is the optical fiber, and the light which is coming from one side to the other side, which is going from one side to the other side, is going. These optical fibers is in not in a straight line, it's not in a straight shape, it is having different curves and bends and everything here, but light travels from one end to the other end because of the phenomena of total internal reflection. If this total internal reflection is not there, light from one end will not be able to reach the other end. You will not be able to see what is inside my stomach. Do we understand this?
Yes, sir.
These are the two applications of there are more application. One more is Mirage. We'll go through the application. Just note it down. I'll give you a minute to note these things down. It's important that you know the examples of refraction, the examples of TIR, because straightforward question is going to come 1 minute. We come to the next point. Next application, Mirage and looming. You must have seen Mirage. Mirage is formed by total internal reflection in deserts, because hotter air which is near the earth's surface has got a different refractive index. It is less than the air above it. Because of that, when you're seeing objects from higher, it is moving from a height. The air here is denser, here it is less dense, so it is moving from denser medium to rarer medium. So total internal reflection happens and the object image is seen like this below it, and that is known as a mirage. I hope you understand the image over here. The image is given in your sheet. I am just trying to show it. This is how light travels. If you have a camel, as you can see, light is traveling from denser medium to rarer medium. It's bending away from the normal, and at one point it cannot go into the other medium. It will be totally internally reflected. So this camel which is here can be seen here. Do we understand this? This phenomena happens because of
Total internal reflection.
total internal reflection. Do we understand this?
Yes, sir.
This is mirage. Similar concept is looming. This is seen. This is seen in polar regions. Same phenomena, same thing happening. This is known as looming. So similar to mirage in desert, in polar regions, looming takes place due to total internal reflection. Here, mu decreases with high, and so the image of object is formed in air. Object which is on ground looks like it is in air, and that is why you see all sorts of what? All sorts of all these UFOs in polar regions and all that. You know, you see image of something in air and you feel that it's a UFO. It's not a UFO, my dear friend. It's probably the image of something which is on ground. Do we understand this?
Yes, sir.
Just gone above our heads. I'll give you a minute to note it down. Then it's my duty to bring you back to some question and answers based on what we have learned till now. This is question number 13 from your sheet, and the question goes like this. A ray of light travels in a medium whose refractive index with respect to air is √2. When the angle of incidence is at an angle of 45 degrees to the surface, then which of the following options is correct? A, B, C, D, 1, 2, 3, 4. What is the correct option? I'll give you a minute to win it. Do I have the answer for this one? Angle of refraction is 45. Total internal reflection takes place. Angle of refraction is 90. The path of the ray is undeviated. Which is the correct option?
Sir, option C.
Option C is the correct answer. That is correct. How do I find it out? I use this formula. Sine of theta critical is 1 by mu. Do we understand this? Mu
Yes,
is
sir.
given as root 2. So 1 by root 2 becomes my sine of theta critical. From here, I can find the value of theta critical. How much is theta critical coming, bacha?
45.
Theta critical, yes, my dear friends, is 45. If the angle is less than 45, it will get refracted. If the angle is 45, angle of if the angle of incidence is 45, angle of refraction would be 90, my dear friends. If the angle of incidence is more than 45, it will be total internal reflection. Which option matches our thing correct? Angle of incidence is critical angle, which is 45, and hence the correct option is, with all clauses, the correct option is option C. Do we understand this? Can I have raised hands from everyone in the class? Okay, I hope you understand this. Let's see if we can redeem ourselves with the next question, which is the next one in line, question number 14, and it comes on your screen. It's already on your screen now. Question number 14, and I wait for your answers. So how to solve this? Any idea, anyone? The critical angle is given as 30 degrees. Yes or no?
Yes, sir.
So from there, I can find the refractive index. Sine of theta critical is 1 by mu, which is now equal to 1 by 2. From here, I can find out. Oh, the theta is given as 30 degrees. Sine of 30 is 1 by 2. From here, I can find out that mu is equal to 2. I just did the ulta. Do we understand this? Mu is equal to 2.
Yes, sir.
Anyone in the class, please raise your hands. That we understand that the value of mu is 2. Now we know the value of mu is 2. We can find out the speed of light in that medium. We know the formula. Mu is equal to C divided by V, where C is the speed of light in vacuum and V is the speed of light in the medium. From here, I can get V is C by 2. Yes or no?
Yes, sir.
So which is the correct option, bacha? Which is the correct option, bacha? The correct
Option
option
B.
is B. That is correct. 1.5 into 10 raised to the power 8. Remember, speed of light is highest in vacuum. This cannot be the answer. This cannot be the answer because there are more than speed of light is not possible. Equal to the speed of light is also not possible in any other medium. The only possible options are 1.5 and root 3. And as you know, if you had to guess, it is 2 out of this one guess. There's nothing to be guessing here. Root 3 is definitely not the answer. The only answer is 1.5 into 10 raised to the power 8. Do we understand this? Can I have some raised hand that we understand this, sir?
Yes, sir.
Let's see who can give me this straightforward question with a straightforward answer. And the question comes on your screen now. Mirages are observed in desert due to the phenomena of, what is the answer for this one?
B, sir.
Total internal reflection. Don't get confused by complicated terms. It is simply TIR. Do we understand this?
Yes,
Yes
sir.
or no? No, yes.
Yes,
Don't
sir.
forget it, beta. We are doing a lot of hard work. You and I, more than you, or more than I, you. So please get the maximum out of this. Here comes the next one. Let me see who gets me this one. And the question is very simple. Which statement is correct? A, B, C, D, 1, 2, 3, 4. You have a minute. to grab it. Yes, bacha. Which option is correct? A, B, C, D, 1, 2, 3, 4. I'm waiting for your answers.
A, sir.
A, it is as simple as it gets. The answer is A. Do we all understand this? Yes or no? No or yes?
Yes, sir.
Okay. Then here comes the next one. The more the number of questions you do, the better is what you are going to become. A cut diamond on an air bubble in air shines brilliantly. Due to what? Due to what? Due to what?
Option C, sir.
Option C, total internal reflection. All of us now know this phenomena and we are pretty confident about it now. So let us move our attention to, I think I'm almost done with all the questions here. I'm just having a look whether I've missed any question or not. Let me see. Here. I think we have done with almost all of the questions. Just give me a minute. I saw a question and I wanted to do that. Okay, this one. Let's see if you can do this one. That will be the last question for today. Here it comes on your screen now. And I'll give you a minute to win it. A small coin. Oops. I don't think you are able to see the entire question. I will have to make some adjustments here. Do you see the question now, bacha? The complete question. A small coin is resting on the bottom of a beaker filled with liquid. A ray of light from the coin travels up to the surface and moves along the surface. How fast is the light traveling in the liquid? Do you see this question? Yes or no? No or yes?
Yes, sir.
Can I have the answers, please? I'll give you a minute, a couple of minutes to solve it. Well, let me solve it. How I'm going to solve it? I have to find out this angle of incidence I. Yes or no?
Yes, sir.
And this angle is equal to the critical angle. Yes or no?
Yes, sir.
I have to find the value of this angle I. This angle I is also same as this angle I. Yes or no?
Yes, sir.
This side is 3 centimeter. This side is 4 centimeter. So this side becomes 5 centimeter. Yes or no?
Yes, sir.
From here, I can find that the value of sine of I. Sine of I is perpendicular divided by hypotenuse. Do we remember this perpendicular? This is the perpendicular. Yes or no?
Yes, sir.
And this is the hypotenuse. Yes or no?
Yes, sir.
So sine of I is 3 divided by 5. Can I have some raised hand that we understand this? So sine of I is 3 by 5. This is also equal to sine of theta critical because the angle of refraction is 90 degrees. Yes or no?
Yes, sir.
The sine of theta critical is 1 by mu. Yes or no?
Yes, sir.
So from here I can find out the value of mu. Mu will be the ulta reverse of this 5 by 3. Yes or no?
Yes, sir.
Now this mu is equal to 5 by 3. From here I can find out the speed of this will be equal to c divided by v, where v is the speed of light. Yes or no?
Yes, sir.
Now can you tell me the answer, bacha? V is equal to 3 by 5 times the speed of light. Speed of light you must know. And the correct answer is, can I have the correct answers? Can I have the correct answers? Can I have the correct answer? Can I have the correct answer, please? And the correct answer is, and the correct answer is, so much time you have taken. Not good. The correct answer is 1.8 into 10 raised to the power 8. 3 into 3 is 9. 9 divided by 5 is 1.4. It should 1.8. It should not require a lot of calculations. This is fourth, fifth standard, not even fourth, fifth standard, second or third standard, not second standard, third standard division. 9 divided by 5 is 1.8. 1.8 into 10 raised to the power 8. That is the answer. Do we understand this? Yes or no? No or yes?
Yes, sir.
Okay, with this, we come to an end of this particular topic. The name of this topic was refraction at plane surfaces. What we have done in this particular chapter, we have seen what is in this particular topic is what is refraction. We have seen the Snell's law. We have seen what happens when light is passing through a glass slab. Everything shifts. The shift is given by d into 1 minus 1 by mu. Can I have some reason that we remember this? We have also seen that when light goes from one medium to other medium, it bends. When it goes from denser to rarer, it bends away from the normal. And if the angle of incidence is equal to the critical angle, the angle of refraction becomes 90 degrees. If the angle of incidence is more than the critical angle, light will not move into the second medium. It will come back into the first medium. This phenomena is known as total internal reflection. We have also seen that sine of theta critical is 1 by mu. Mu is C by V. Do we remember this? Can we keep all this data in our heads?
Yes, sir.
Yes, sir. Then, sir, in the next class, sir, we'll move on to the next topic, sir. I have done almost all the questions that are possible to come. The next class, we'll be dealing with one more interesting topic. We'll be dealing with refraction. Plane surfaces are done. Now we'll move on to the curved surfaces. Refraction at curved surfaces would be our next topic. I'll see you in the class tomorrow. I hope you find this class interesting. Take care. Have a nice day. And may God bless you all. Bye-bye.
Bye, sir.